Okay, so today I will be talking about the fat amplifier. Okay, the fat are commonly used to amplify small AC signal. One reason for using the fat instead of a bipolar transistor, the thing you get a very high input impedance, G in, can be obtained. A big disadvantage, however, is that the voltage gain often with the fat is much smaller. Okay, so basically we already know we get a bipolar transistor. Okay, and bipolar transistor you can get amplified CE, common emitter, CC, common collector, and CB, common base. Okay, for the bipolar transistor you can get a higher gain. However, the input impedance is not really good like the JFET, okay? And also, JFET amplified configuration are as follows: common source, common gate, and common drain. Okay, still same thing, a three amplifier. Now, this is the way how to go to the detail for AC analysis. That for both either bipolar transistor or JFET. Number one, you have to set on the DC, okay? Source, that means the DC power supply, to zero, okay? That means on off the DC power supply will be routed and replace them by a short circuit equivalent. Number two, replace on capacitor by a short circuit equivalent. You know, you get a capacitor will be a DC blocking or AC coupling or bypass capacitor, okay, in bipolar transistor amplifier. Remove all element bypass by the short circuit equivalent, okay, and introduced by step number one and step number two. Redraw the network in a more convenient and logical form. Now, the first one we're talking about will be a common source, okay? Common source amplifier. Okay, so this is the JFET in AC. They not look like that. Okay, this is for the DC. For the AC, you can see you can get a gate in here. Okay, this is the source, and this is the drain. Okay, this is from gate to the source. That means VGS. Okay, only thing is This is the internal, okay, output resistance. We not deal with that. They not using, okay? So we'll see. That input impedance, okay? That means when you're looking into the input here, input impedance almost infinity ohm. That's telling you the input impedance very high. Output impedance, okay? So basically right now, they're talking about that resistor right here, okay? We're not using that anyway. Later on, when you connect the load, then you could be see that, okay? If they say R small d, that means our internal output impedance not using. Okay. So from the drain to the source, you get a current source. And the value will be Gm times VGS. So basically, this, this is the basically the effect for AC. And this is the JFET for DC. Okay, now this is the amplify. Okay, you can get the input here. Okay, and this is the output in here. Okay, so before we want to do anything, you understand me? JFET, they already get the DC bias. Okay, last time we already talking about DC bias. Okay, the fourth bias will be a fixed bias. Okay, fixed bias. The second thing, they can be a cell bias, and then they can be a voltage divider bias. Before we can get to an amplifier, on of those bias have to be no problem. So when you see on this circuitry here, what bias we using? You know what bias we be using for this amplifier?
It's fixed?
Fixed bias. Correct. Okay. You see, you get a DC voltage here. Okay. I've given you the example. If I get 2 volt, RG equal 1 mega ohm. My question is, what the get VG equal?
Is it 0 volts?
What VG equal? Okay, you understand it, the current flow through RG equal 0, right? Correct?
Correct.
The thing is, the resistance is too big, so no current. So that will be telling you VG and VGG will be the same, correct? The thing is they not drop any voltage. So the answer will be equal minus. Is it right? And you already know V, G, F equal what?
VG minus VS.
Perfect. VG minus VS. And VS equal 0, right?
Yes.
Okay. So okay. So that means you can get VG equal minus 2 volt. Okay. Now we're talking about common source. They're telling you input signal apply to the gate. That means input signal here. That is the sine wave. Okay. What the name for the capacitor C1 and the purpose using C1? C1 will be DC blocking and AC coupling. What that mean? That means they not allow any DC voltage from the input go to the amplifier. And they allow only AC. So that's why on this side here, you can see you can get a sine wave go through it. Okay?
Yep.
And C2 will be the same. That means DC blocking, AC coupling. Okay. At the drain in here, same thing like bipolar. Okay. You can get two types of signal. First thing you can get a VD. That means dry, voltage. And also you can get the sideways. So when you go into the output here, normally connect to the speaker. And the speaker, you don't want any VD, DC. You want only the sideways. So that's why we need capacitor C2 to block VD. Allow only the sideways coming out to the output. Okay? Now, input impedance. You can see right here. That means from the input signal looking into the amplifier. Okay? Then, whatever resistance you get, that's the input impedance. Okay? And the output impedance. That means from the output looking into the amplifier. No matter what resistance you see, that will be output impedance. So you say basically the bipolar or the JFET will be the same thing. You have to deal with the input impedance, output impedance, okay? AC coupling, DC blocking, capacitor. These are very, very basic. You want to looking for the technician job. This is the interview they will be asking you. They're not asking you to do calculation. They're just asking for your understanding. When you're looking into the amplifier, you have to tell what type, what the name of this amplifier. Okay? Common source. Common source amplifier. Input applied to the gate and output from the gate. Okay? Everything we already delete in here. See, that's a summarize. You're looking over, okay? More time. Then when you memorize it, then you can talk right away.
Mr.
Okay.
Cram, what's the phase?
Here, number 3, input, output is our phase. That at least you have to know, you have to memorize it, okay? If you go up to the engineering, then they can go to the calculation, more detailed. However, we don't have to go through calculation, okay? Any question up to this point about common source amplifier?
So it's 180 degrees out of phase, right?
Right, that's what I said. You see that? I already in here. Input, output is our phase. If they asking about what the bias, again, I'm telling you, we get a fixed bias, we get a cell bias, and a voltage divider bias. Okay? And what is the input? If you're looking into that circuitry here, what input? Impedance equal I can telling you, this is one here. Okay? 1 mega ohm in this situation. That's the input impedance. Okay? And the output impedance, when we draw it, you can see. However, up to this point, any question about the common source amplifier?
Yeah, Mr. Pham, does it have a gain?
What?
Does this amplifier have a gain?
Yeah, we're not going to calculation yet.
Oh, okay.
Right now, what I expect you see the amplified circuitry. You have to say, this is a common source amplifier. That's the first thing. Second thing, input applied to the gate and output from the grid. Input output will be 180 degrees our phase. At least that's what you have to know.
And how you can tell it's a common source is it's gate to drain. So VI minus VO, right?
You're talking about what?
Gate to drain equals common source.
Okay. Gate and drain, common source.
Gate to drain equals common source. It's just
Yeah.
the way when you're looking at a circuit, how you could tell, right?
Okay, yeah, you have to know where is the input, V in. Where is the output, V out. For the common source, input applied to the gate, output from the drain. Then you know that a common source amplifier. And a little more input and output is our phase, 180 degrees. At least that's what I think we have to know up to that point. Now, this is given you a little more detail here. Where is the battery? See, this is the battery, minus 2 volts, for example. And we already know, they're telling you, power supply will be shorted. Okay? They say battery VGG replaced by shorted. That means shorted to the ground. Okay? Second thing, capacitor C1. You see that? C1 will be shorted. That's what they already telling you from here. Replace on capacitor by a short circuit equivalent. So that's why it is shorted. They pass only AC and were blocking for DC. Now, This is the input here. And this is the gate. Okay? This is the source. And this is the drain. Okay? Now, we're looking for the battery. Okay? VDD. You can see VDD. Same thing. DC will be sorted. So that's why they sorted throughout. So what happened to RD? RD, one side connect to the drain, the other side connect to the VDD. Then you can see, okay, RD here, one side connect to the drain, the other side connect to VDD, VBB, no VDD. And now that will be sorted so they connect to the route. Okay, and from the drain to the source, you get the current source, and the value will be Gm times VGS. Okay, internal resistance, okay, they supposed to be in here, but we're not using, okay, we don't care that. So, if you're looking for AC module, what the input impedance? G in. What is in equal?
Is it RG?
RG. That one.
You beat me to it.
Okay. What is the output impedance? G out.
RD?
RD. Perfect. When you're looking from the output to the amplifier, you can see right now you get RD. That's what we call output impedance. Okay. So this is a more detail, okay, for AC module of the common source amplifier. Any question? Anything? That's more simple than bipolar transistor. Now, this is the source right here. This is the input impedance. Okay? And this is the drain. And the resistor here will be RD. Okay? And this is the current source from the drain to the source. The value will be Gm times VGS. Okay? Now, calculate the voltage gain AV. Okay? V out. If you want to calculate the V out, that means the V out here. Okay? From the drain to the ground. So V out will be the current here. Gm times VGS times RD. Okay? My question is, how come they say minus Gm? You know GM times VGS, that's the current source from the drain to the source. They show you right here. Why you get a minus sign? Who can tell me? How come you get minus sign? GM VGS time RD.
Is it because it goes to the ground?
Through the drain?
Okay, you understand A, the current GM time VGS, this current, right?
Mm-hmm.
Okay, now V out, this is a V out. If I given you a meter, I want to measure V out. That means one side you connect to the drain and the other side you connect to the route. Okay, that will be telling you one thing. You want to measure V out. You go this way, right?
Mm-hmm.
They opposite to the current,
Yep.
GM times VGS. So that's why you get the minus sign right here. Okay? And then they say VGS, that means VGS from here to here. Okay? Equal V in. Okay? VGS equal V in. That will be telling you V out will be equal minus V GM time V in time RD. Okay, then the gain will be equal. Okay, minus GM time RD. You see, this is common short amplifier. Very more simple than the bipolar. Now, if they say, if they get a loading connect here, if you get a loading here, RL, then output impedance will be equal RD and RL in parallel. Okay? That's what they're telling you here. If the load, okay, including, then the gain will be equal minus GM time RD parallel RL. So that covers everything for common short amplifier. The effect. Any question, anything? Okay, if it's not, we go. Let's see. Okay, now you do it, this problem for me. First thing, the fixed bias configuration of head and operating point defined VGSQ. like we already telling you. Okay? We already telling you VG equal minus 2 volt. Okay? And you know VGS VG minus Vs. And Vs equal 0. So that's why VG equal minus 2 volt. That's what they're talking about VGSQ. Okay? And ID. Okay? Equal 5.625 milliamp. And IDSS equal 10 milliamp. Okay, my question. What is IDSS? Who knows?
Is it the current from the drain to the source?
I just talking about
It's the maximum drain current.
I talking about definition.
It's the maximum.
IDSS.
It's IDSS is the maximum drain current.
That's close, but it's not quite. Basically, if you're looking back at DC bias, IDSS, that means the maximum current with the VGS of equal
0.
10.
Yeah. Sorry, I should have said that as well.
And the IDSS, that means the current from the manufacturer. Okay? They make the JFET, they given you IDSS. You cannot doing anything with that. Okay? And the VGS off, they given minus 8 volt. That normally for a JFET, they will be given you two things here. IDSS and the VGS off. Okay? Equal minus 8 volt. VGS off. The thing I did, I get the information from one of the university, but they get it wrong for VGS off. VGS off is minus 8 volt. VP and the VGS off will be the equal value, but opposite polarity. Okay? VP positive, VGS off negative. Okay? And manufacturer, they given you only one value. either VP or VGS off. If they given you VP, then you know VGS off. Same value. Okay? Only thing is opposite. In here, I'm telling you they wrong. The thing is they say VP equal minus 8 volt is wrong. They have to be equal plus 8 volt. Then VG at off, they will be equal opposite. That means minus 8 volt. Okay. Now, they want to know GM, train conductor. Let's see, I get a formula or no. I try to get the formula GM.
The formula is on last week's handout also.
Right, I know. Okay, we have to go through the last one. Now, let's see. Okay, let's see. I can give it to you. Okay. Okay, GM equal GM0 time 1 minus VGS divide VGS of okay.
It's VGS on top too. VGS.
Thank you.
Mm.
Okay, GM0 equal 2 times I D SS divide VGS of Okay.
Yes.
So now you can calculate the GM0. They already given to you 40, right? Michael Silent.
Yes.
That's what I hear. Okay. So go ahead and calculate the GM for me. So GM equal 40 times 1 minus VGS
-2 volts,
negative 2 divide
-8. Mhm.
negative 8. So see what we get. Is it you can get what value?
Yes, that's it.
Okay.
Mm-hmm.
Number B, we're not working. That means they want internal resistance. So we don't need to calculate that.
Hey, where would baby RD be at on the schematic?
On the schematic,
Yeah, where would it be located?
Hmm.
you mean here.
Yeah, baby RD, yeah.
Oh.
A little more detail here. You see that?
Uh-huh.
So
But
it's one over that resistor, right?
yeah, internal,
Oh,
Mhm.
internal,
Uh-huh.
internal.
inside the JFET.
Okay.
Okay. And basically, they will be equal 1 over. Okay, lambda OS. That's given. See right here. But the thing is that's too big resistance. So that's why on the calculation not using that. Okay. They want the in
1 mega ohms.
1 mega ohm. Perfect. You can see right here. G out.
RD, which is
G out of here, right?
Mm-hmm.
You're looking into amplifier. What impedance?
So would it be 2K?
Perfect.
Yeah.
Because you're going to short out the capacitor.
Exact. Short. That is short 20 volt to the round. So the drain to the round will be 2K.
Yep, there it is.
So the answer will be 2K.
Yep, up above.
You still get a very good memory.
Good eye, Joseph.
He was talking about you.
Oh, thank you.
You're the star of this class.
Yeah, they're really working hard. Okay,
You should put her on your staff, Mr. Pham, like Sam was.
exactly.
Yeah.
If they change something and they need asking back the assistant technician to the program, yeah, then it can be.
Put her in.
It's hard to say anything.
Uh-huh.
But like Sam, you see that?
Hmm.
They offer for the full-time employee.
Wow,
And
that's
now,
amazing. That's amazing.
yeah, when I interview, we get around my dean, myself, and one other instructor, okay, and two more people from a human resource. And when we interview, okay, we get three engineers, okay, and Sam. And they come in and we ask questions, they answer. However, I let them know I want, whoever they allow. The thing is, I run the program. The other instructor apply for the job, they be an engineer, but they not working on a level. So we don't want the time to training them. So that's why we hire Sam. He get a full-time employee, get all of the benefit. Okay. So when the COVID-19 happened, okay, the program is much smaller. So that's
Mm,
why
yeah.
they move him to the ECC center to working on the other department. Okay. Now when they coming back, then I have to get the assistant again.
Yeah, new approval, huh?
Right, for sure.
Yeah.
So only thing is, who I can trust, who I can believe in. Okay, then they can help the student. I try to try now. I try for the technician too. You can do like I do it. Then okay. Technician one more easier with the left phone, right? You already know how to do a left phone, no big deal. But for the textual digital, asking for real technician when they get a problem, how can we help? Even I get to lab instructor in the program, but so sometimes very hard for them. Okay?
Yeah.
To me, that's no problem. Anything I can know how to do it, how to solving it, how to help you to solve the problem. Okay? Anyway, Now, the next one, they want calculate the AV.
VO over VN.
AV, they already gave you formula here.
Bless
Minus
you.
DM times RD.
Mm-hmm. So 2 kilo ohm over 1 mega ohm.
Yes. You minus GM time minus GM time RD. So now you can calculate that.
Hmm.
You already got the GM. You know RD. RD have to be in ohm, right?
Mm-hmm.
And
Yep.
that's why you can calculate that. Okay? And the last number, they want AV. Okay? Ignore RD. So basically, we just already calculated without RD. So you can see for this common source amplifier, very simple. Okay, and it is just they given you not a picture. Remember, we don't care that.
Hey, Mr. Pham, that one you just marked out. So basically, you're saying that little RD is Mr. Pham.
Internal
Yeah. Can you
resistance
go back? Can you go back to that?
right here, right?
No, no, no. The other way. The other way. The, oth- the other way.
You're going the wrong way.
Okay, I'm talking about RD first.
I
Oh,
know, Mr. Pham, but when I asked the question, you scrolled. You went away from what I was talking about.
Here, right?
Up a little more. A little more. Up. You got to go
Up.
up the other way. The other way.
What do you mean the other way? Here?
You keep going. You keep going. Go back. Go back.
what page?
Keep going. Keep going. Right there. Right there. Right there. Okay. So basically, you got like little RD and big RD in parallel. But
But
you're saying, let me finish. You're saying little RD is so big, the magnitude of little RD is so big, it's insignificant. So that's why you just go with RD, big RD only.
exactly.
It's
Okay.
like if you parallel two resistors. If you put a resistor and two resistors in parallel, and one of them is 100 ohms, and then one and the other one is a billion ohms. Well, it's going to take the smaller one.
Okay, now if you see, if you get resistor parallel, one 10K, okay,
Right,
KO, okay, parallel
right.
with 1K.
Right. It's going to be,
Combine two resistors in parallel. 1K times 110K divide 1K.
yeah, the answer is going to be smaller than the
Yeah.
small one.
That will be a 10K divide 101K, right? 11K.
Mm-hmm.
So basically, they almost 1K. That only telling you if two resistors in parallel, one will be too big. Okay, so basically they don't care about that too big.
Yeah, right.
Okay,
Hmm.
now next circuitry. Not much thing to talking about that thing. Okay, so basically common source here. What is the difference? The difference will be they adding capacitor. Who remember the name of this capacitor?
Self-bias.
By part,
Oh, you talking about the C3
right?
or
Oh,
CS. Yeah, CS is a bypass capacitor. The other two are coupling or DC blocking.
This one is DC
Blocking.
blocking, AC coupling. This one same thing.
Yeah,
Now AC to go, not DC.
right.
However, that C3, okay, they say CS, that will be by part capacitor. My question is, what that capacitor by part?
Bypass DC, you mean?
RS.
Yeah,
Oh, yeah, RS.
that only telling you. Right here you get the DC voltage, okay. However, when you get the AC, then you suppose you get the AC here. And the capacitor will be short for AC. So that AC not go through our head, go to capacitor and to the ground. That's what they call a bypass. Bypass what? Bypass resistor RS. Okay. Now, looking into that circuit, what type of bias?
Yeah,
You mean like self-bias?
it's self.
Bias, correct? That's what, when we're asking the guy, at least you have to know. That's just a basic. You have to go through the handout, looking over. You can say, how come I cannot follow it? I want to follow it, I cannot. I'm looking at it right away. The thing is when you already understand, okay, then you cannot forget it. Good. The thing is the gate. You see, this is the gate. And the gate connects to the resistor to the ground. No DC power supply. So cell bias. Okay? Again, for cell bias, if you want to do calculation, that means you need a graphic. However, they're not using graphic for the technician. So that's why they have to give you something. I'm telling you, they given you Vf equal 1 volt. Okay? That's what they given. Okay? So that's why you don't have to using graphic. Okay? Vs equal 1 volt. Can I calculate the Is? What Is equal?
IS is equal to 1 volt divided by 200 ohms.
Exactly. Vf divide Is. 1 volt divide 200 ohm. Okay. Now, who can telling me what ID equal?
ID, it's the same.
Perfect.
Because you said for the JFET, IS and ID is the same.
Same. Yeah.
Perfect.
Mr. Pham tried to trick us.
That means for the JFET on the time, ID, IS will be the same.
Hey, Mr. Pham, I got a question for you. I think you said it before, but maybe I need to hear it again. See where you got the G at for the gate, where you wrote G for the gate?
Yeah, G for the gate at here.
Yeah. What happens if you take that resistor out?
Same thing. The voltage from here to here. Okay.
From where to where?
That means you have to get the voltage from here.
We can't see,
We can't,
your blinky isn't working.
you need to use your little marker so we can see what you're pointing to.
Okay, VGS, right? Equal VG minus VF. Is it correct?
Yeah.
Mm-hmm.
And VF we already calculate, right?
Mm-hmm.
They already given you 1 volt. So that's why VG minus 1 volt. Okay. So VG will be equal 1 volt.
Yeah, but my question is, Mr. Pham,
Yeah.
if you look at the circuit, what happens to the signal, to the AC signal, if you take the 1 meg ohm out?
If you take the 1 mega ohm out, so basically when they short that one to round.
Right.
So the sine wave will go to the round, not go
Okay.
to the gate.
Oh, when you put the resistor there, that's to prevent the sine wave from going to ground.
Right.
Okay, got it.
So that's why they have to put a big resistance here. Okay? So the sine wave can go to the gate here.
Okay.
Okay, now let's see. If they asking about input impedance, G in, that means they looking into it.
Yeah, that's the 1 meg ohm.
Yep.
Okay, this one. Right?
Mm-hmm.
Right.
Okay, now telling me G out. G out you're looking into here.
So you got, that would be 10K in
Okay.
parallel with 1.5K.
Yeah.
Right. 1.5K parallel 10K. If you do calculation, it will be 1.5 times 10 divide 1.5.
Plus 10.
You see that?
Mhm.
Now, the next question.
20.
How come we need bypass capacitor? How come we need that guy? Who can answer me?
The source.
Remember, this is talking about bypass from bipolar transistor amplifier.
Right.
Which capacitor are you talking about?
Bypass.
The bypass.
Oh, okay. So that's the one where you said you wanted the AC to pass, uh,
Yeah,
bypass RS.
Bypass, yeah. So it could.
but the question is, why do we need that capacitor?
So it doesn't get impeded by the resistor.
That is how they working. But the reason is, how come do we need to connect the bypass capacitor?
Because you don't want the DC involved.
Now,
That's what it's bypassing.
Yeah.
It's bypassing RS.
yeah, however,
The source. It.
Because you want a clean AC signal?
now,
That was a good try.
Yeah, I like that. I like that a lot.
okay, the reason we need the bypass capacitor, the thing is, we want the gain little higher.
Yeah.
That coming out from bipolar transistor.
Oh, you want so this, we're talking about FETs or field effect transistors, and you're saying that bypass resistor in this circuit for field effect is gives a higher voltage gain than what a bipolar transistor would.
Same thing. They just get want to get a more gain. Okay? So when you're looking into the circuitry now, you look like you're able to understand whatever going on here. That means perfect.
Hey, Mr. Pham,
Yeah.
then the question becomes, we have what is called bipolar transistors. That's with the emitter, collector, and the base, and then we have field effect with the drain source gate. So is the field effect a better transistor, or we use it because voltage gain, you get a better output?
Now, field effect transistor get less gain than bipolar.
Oh, it has less gain?
Yeah.
So then why do, because nowadays I think I've heard you say they use field effect transistors more. So if it has less gain, why are we using it?
Now, the thing is, they first get the high input impedance.
Okay.
That is why. That's the only thing different from bipolar. Bipolar get a higher gain.
But low input resistance.
Yeah. They
Okay.
get only different from bipolar. The thing is they get a very high input impedance.
Okay.
You know why we need a high input impedance?
Tell us why, Mr. Pham.
That will be telling you one thing. Your voice, that's an AC signal coming in. Okay? If you get a high input impedance, so you don't lose that your signal. Okay? And the other amplifier, they not get a high input impedance. That means they get a voltage divider or whatever. Okay? That your signal coming in have to be divide something. Okay? They don't want that. Most of the circuitry at this time, instead they're using bipolar, they're using JFET. So that's why I said JFET is very, very important. When I study engineering, at this time they don't have a JFET. So I don't know anything about JFET. However, when I'm teaching, I have to talking about JFET. So that's why I have to understand anyway. Okay? So this is a redraw the other circuitry. And they will be asking you to calculate the same thing in that one. Okay? A lot of calculation. And we will be going to the detail after we get through that thing. Okay? And now on that one, also they given you the signal. This is the input here. This is the output. You see that? They will be our phase. 180 degrees. That's it. This just a summarize. Okay? We don't using anything for RD. This formula, we don't need that. The thing is, this lecture, they prepare for engineering. So that's why. Okay? They summarize for you here. GI, input impedance, equal RG. G out, okay, equal RD. The thing is we don't have a load, okay? And this we don't care now. That only thing. Just summarize. And finally, they summarize for the gain. Okay? That only the gain. That only the formula you're using. That one we not. The thing ở đây include RD. Okay. Cần common source amplify. Okay. Configuration at a 180 degree phase shift between input and output. This just a calculation. Okay. Next time meeting, we'll go to calculation. Okay. Same thing. Okay, next one. Common drain. Okay. Common drain. Amplify. Input apply to the gate.
Output from the source.
Output
From the source.
from the source. Okay. And also they get another name. Source follower. That's only telling you signal at the source or signal at the VOut, same thing. Okay? If you get the signal at the source, then you get the signal at the VOut. That's why they get another name, source follower or common drain. If you're looking into this circuitry, what the DC bias?
Oh, you mean self-bias?
Perfect. Cell bias.
A fixed bias has got to have a battery in the thing, right?
Exactly. If you get a battery here, that means fixed bias. Okay? This is a cell bias.
Self-bias.
Okay. Common drain. Amplify configuration. The input is on the gate. Output from the source. Okay? When you're looking into the amplified circuitry, you have to know what is the name. Okay? So basically, you can see this is the AC. The gate, the drain now will be round. And that will be the source right here. Okay? And they already telling you input impedance. That means this resistor here. Okay? And output impedance will be calculated by RS parallel with 1 over GF. And also, they given you the formula to calculate the gain. If you want to calculate, then you just using the formula. Okay? Now, let's see. In here, only thing is they're not telling you. Okay? Here, they do. Common drain. Amplify had no phase shift between input and output. Okay? That means they will be same phase. This is just the calculation Okay, and they already given you every formula here. What EL equal? Okay. Remember, when you apply the formula, anything you see RD, don't use it. Okay. Next time, I have to delete that. The thing I did is from university. They teaching engineering. So that's why they go to calculator, internal output resistance. Okay. Okay. So basically, that will be doing calculation. Okay, just remind you here. Circuit below, so common drain. Amplify usually refer to source
Source power.
Source follower.
either name. Okay. Source follower has a high input impedance, low output impedance, and a voltage gain of less than 1. You see that? Not much gain. Okay. So when you're looking into the circuit, you know this is a common drain or the source follower amplifier. Okay,
Mr. Cram, and you said this is unity gain?
not unity gain, but they can be unity or less. Little.
Okay, unity or less.
Okay, and they get a high input impedance and low output impedance. Want the gain less than 1 or unity. That's the only thing I want to memorize. You're looking into the circuit. You know the bias, cell bias, fixed bias, voltage divider bias. For the cell bias and voltage divider bias, you want to solve the problem. You have to using the graphic to avoid using the graphic. They have to give you something. For example, for this is a cell bias, they given you Vs, 2 volt. And when you get a Vs 2 volt, you can calculate the Is. Is equal Vs divided to Is. After you get the Is, that means same thing like the drain current ID. Okay? Okay, so this is just an example. We will be going through that. Okay? After first week, when we return, try to make sure if I given you the formula, you're able to calculation. Okay? Common gate. We already go to common source. Common drain. Now the last one, common gate. Okay? Input here. Output from the drain. So input applied to the source. Okay. Output from the drain. Okay. Common gate configuration. That means the gate will be routed here. The input is on the source and the output on the drain. Okay. If you're looking into the input impedance, same thing, right? You get RS. Okay. And now you see in the circuitry here, RS input impedance. Okay. Output impedance. Okay. RD. And this is the current going from the drain to the source, Gm times VGS. And also, they given you the formula. What input impedance? G in. Okay. Now G in will be equal RS parallel to 1 over Gm. Okay. Output impedance in this case equal RD. Okay. And this is the gain Gm times RD. Common gate amplify had no phase shift between input and output. To say to take the same thing in bipolar transistor. Bipolar only common admitter, input output are of phase. Common collector or common base, input output same phase. And now in the phase amplifier, you get the same. Common source, input output out of phase. Common gate in phase. Common drain in phase. Okay. So you're looking on that one. Input apply, let's say. That is gate. That is source.
Yep.
And that is the drain. Okay. So for the common gate, input apply, okay, to the source. Right here. This is the input applied to the source. Output coming out from the drain. Okay. And any calculation here, we already get the formula. If you get the time, okay, you can try by yourself, okay, try to calculate to see, okay, when we get a meeting, you get the right answer or not.
Hey, Mr. Pham, well, go back. You just said the input go to the source and output go to the drain, and this is a common gate, right?
Right.
Okay, then how come up in the green, that green area in the upper left, it says JFET common source amplifier? Shouldn't it say
No. Okay, I understand. This is a title for the whole thing. This have to be changed.
Oh, it's a typo.
Yeah, title.
Okay.
We'll correct that.
Yeah, because all of that stuff says common source for everything.
Okay, we'll correct that.
And then another thing, Mr. Pham, go back right there. No, go back. Right there, right there. No, you keep going back, Mr. Pham. Go back a little more. Go, stop, right there, right there.
Okay.
Okay, where it says source, that's where the input signal is at, right? The AC input signal, where the S is at in yellow.
Oh, input signal here. Right?
Yeah, draw the sine wave. Draw the sine wave for the input and output
Okay.
so we can see it better.
It's after C1. Yeah.
Okay, so that's and then the output.
That's the input signal coming the
Now draw the output one.
To the source.
output
Source.
here. Okay.
Yeah, okay.
They will be the same phase.
Okay, same for, all right, there we go. There we go. That's what I was looking for.
Okay.
Okay, thank you.
Good job.
You're welcome.
You
Next
you
time-
fast, Mr. Pham, turning those pages.
Next time I see you guys, you can understand more.
Uh-huh.
Get the time to review. This time, some people, some students from TechJo, I recommend, better learn that. So that's why they come in, but they still memorize that very good. That's just a summary, okay? That's it. That's for today.
Okay.
All right.
Okay.
Well,
So
thank you very much.
you're welcome. Basically, I hope all of you guys will be getting good holiday, okay? Thanksgiving.
You too. Happy Thanksgiving, everybody.
All right, Mr.
Thank
Pham.
you too.
See you when we get
Okay.
back.
Have a
Thank
good night.
you.
Yeah, we'll see you later.
Okay.
Okay,
Have a good
bye-bye.
week off.
Bye-bye, bye-bye.
Thank you,
Bye-bye.
Professor. Happy Thanksgiving.
Thank you.
Bye-bye.
Thank you.
Bye.